Hello and welcome everyone. Thank you for joining our virtual event today. My name is Alexandra Marsh and I'm the technical author at Andor Technology, and I'll be your host for today's presentation. Today we are talking about mask, making aerosol safety known, and I'm joined by today's speakers, Alan Giltinan and Dr. Niall Smith from Blackrock Castle Observatory. Alan is a co-founding member of Blackrock Castle Observatory. He has an MSci in Applied Physics and Instrumentation from CIT, with expertise in computational and instrument physics. He has experience in both the pharmaceutical industry and astrophysics research, with particular focus on automated and precision instrument systems. He has several publications ranging from SPE proceedings to Institute of Physics papers, and has also contributed to a book, plus a number of posters and presentations internationally. At BCO, he has overseen the development of several high-precision instruments, collaborated on the development of leading photometry software, including some of the first cloud-based photometry analysis tools for research. He also oversees IT services for BCO and the technology for the outreach program, which continues to be developed, deployed, and maintained at BCO. This includes interactive exhibits, custom projection systems, the planetarium, and other similar research technologies. As well as the Center Manager and Chief Technology Officer at BCO, he remains a scientific content advisor and developer at BCO. Our other presenter today, Dr. Niall Smith, studied astrophysics at University College Dublin and graduated with his PhD in 1990. He lectured at the Department of Applied Physics and Instrumentation at the Cork Institute of Technology for 18 years before becoming the Institute's first head of research in 2005. Now providing strategic oversight of a budget of 16 million per annum across disciplines from science and engineering to arts and music, Niall is co-founder of the internationally award-winning Blackrock Castle Observatory, which has just celebrated its 14th anniversary and over 1.2 million visitors. In 2017, Niall was the host director for the International University Space Studies Program, which is the largest conference program to ever come to Cork, lasting a total of 9 weeks and involving over 320 global space experts. Niall's research focuses on space topics including ultra-high precision photometry and the uses of small satellites in low Earth orbit for a wide range of functions, from high-resolution imaging to space cybersecurity to rural broadband. He recently was awarded the Science Foundation Ireland Research Image of the Year Award on behalf of a multidisciplinary team for an investigation into the efficacy of masks against COVID-19 using techniques developed in the astrophysics domain. He was the higher education representative on the National Steering Group for the Irish Government's Space Strategy 2019 to 2023, and considers Space 4.0 to be a significant opportunity for business and educational communities across the globe. Welcome both. Just a little housekeeping before we get started. You have all joined this presentation in listen-only mode, and if you have any questions during the presentation, please type them into the question box in the control panel as we go along, and questions will be answered at the end of the presentation. Now, without further ado, I will hand over to Alan and Niall.
Thank you very much, and welcome and good morning all. I hope you're all keeping very safe on this very topical subject at the moment. The project itself is called MASK, so Making Aerosol Safety Known is effectively what the acronym is. But we're using an astrophysics technique, so you can tell by the introduction that myself and Dr. Niall Smith are more on the astrophysics and astronomy side of things. So what I'm going to do is I'm just going to give you a brief overview of what we do and at Blackrock Castle Observatory, which is part of Munster Technological University, and why it actually was beneficial in the understanding of masks, and how the software and hardware that we have become accustomed to was applied to the understanding of mask efficacy. So at Blackrock Castle Observatory, so we're experimental physicists. So we love, hardware and software. We love getting our hands dirty and getting screwdrivers out and so on. That's kind of the nature of what we do on a day-to-day basis. But then we also, when we acquire the images, we have to analyze them. We develop software platforms and algorithms and manipulate the algorithms and develop the algorithms into formats that actually give us optimized results. I'll go a bit further into that as we go along in the presentation. So the first thing, and I won't stay too long on this, but is what do we study? So we have three kind of main areas that we study. The first is quasars, and we study a kind of a category of active galactic nuclei called blazars, which is kind of, if you're looking straight down into the supermassive black hole through the cone that comes up from it. So we look down at that, and on some images that you're going to see later on, you'll notice the difference between what we see and what other telescopes can see. But there are techniques being developed and continue to be developed in order to understand that, and they are actually applicable with the likes of the cameras that Andor make, for example, and larger telescopes and even smaller telescopes. So it's a combination of both the software and the hardware, which is optimum. But we also look at near-Earth objects and extrasolar planets, and we've developed techniques that kind of reduce the impact of atmospheric turbulence, which ground-based telescopes generally suffer compared to space-based telescopes. So we've developed photometry software techniques that actually enable us to optimize the signal-to-noise ratio and get the best results. So we develop, as I said, photometry. Photometry, for those who may not be familiar with it, is the measurement of the brightness of the object. So basically the number of photons that are arriving at your system. So that's primarily what our physics background is. How do we do it? We use instrumentation. So we develop instruments using the likes of the imagers, filters, the telescopes, the multiple imaging systems. So our dual photometer, for example, which is a multi-filter system. Simultaneous multi-filter system. So we can look at the same object in two different colors simultaneously, which will allow us to, again, differentiate between atmospheric effects. And finally, what we do is we use computational analysis. So we develop algorithms and modify them and update them, because there's always new algorithms, there's always new software patches, there's always something going on, especially with the likes of artificial intelligence and machine learning and things like that coming along, that will allow us to optimize our techniques. Supermassive black holes. So here's one example of one. So this is a Hubble image, as you can see, and you can see on the right hand side, you can see a close up of it. So this is called an accretion disk, and that's effectively where it spirals into the black hole itself. Now, what you get, if you look on the left-hand side, what happens is, as it spirals in, some of the material gets caught in a magnetic field and get propelled away. And so you can see the two kind of jets that are propelled away from it, and they're generally perpendicular. They're not exactly always directly straight in terms of perpendicularity, and they can meander around, and then they go to kind of what's called radio lobes towards the outside of it, and they can be absolutely enormous in size. So what we do is we look at particularly objects that if you take that image on your left and you were to rotate it and look straight down, that's what a blazar is, and that's predominantly what we look at, blazars. So near Earth objects. So you can see here there are a number. So the first one on the left-hand side with the least number of green dots was taken in approximately 1950. Now, if you look at the right-hand side, which was taken in the 90s, late 90s, you can see that there are a lot more near-Earth objects. So near-Earth objects are comets, asteroids, and so on. There's a lot more in our vicinity than we actually thought. So we need to continuously monitor them. So we just keep an eye out for them in the night sky, using our telescopes, but also using our again, the optimized photometry technique, because it's not something you'd necessarily easily pick out in a single image. You need to have the imaging software behind you to be able to understand what you're looking at. I'll skip through the slide because this is a video, I think. Yeah. So stellar photometry. So if you go back, if you recall the image I showed of the supermassive black hole, this is what we normally look at when we're looking at, from a ground-based telescope, this is what it normally looks like. It looks like a normal star, hence the name quasar, which is quasi-stellar, stellar-like. So this is what it generally looks like. So on the right-hand side, you can see a profile of what that would look like on your imager. What's important to understand when it comes to photometry, and especially our type of photometry, which is optical based, it's all optical based, is that the more frames that we get, the higher certainty that we can be, or we can state that we are taking an accurate measurement. So being able to use an exon for or something like that, a high-speed detector with effective zero readout noise on the back end of a large telescope allows us to take a significant number of frames. In fact, we've taken millions of frames in a very short space of time at various different sites. So having that number of frames allows us to then be more certain about what our results are going to tell us. It also gives us the capacity to say with certainty, a high certainty, that the noise levels are zero and that the signal level is high. So this is exactly what our object is doing. Is it varying? Is it not varying? Is it getting brighter? Is it getting dimmer? Another element to what we do is source identification. So this now goes into, so if we move beyond the hardware side of things and we go into the software element of it, we do a number of algorithm identifications and algorithm developments where we extract from one frame, we isolate the areas of interest, and then we analyze those areas of interest. So we do source identification. So you can see on the left-hand side would be a typical image. On the right-hand side is the extracted image. So we looked at point spread function analysis, and we looked at Gaussian fit analysis. And from passing this through hundreds of thousands of frames, we came to the conclusion that the Gaussian fit, which is the right-hand side, gave us the best result. We were able to extract the objects of interest much more readily using the Gaussian fit as opposed to the point spread function fit. So that's just one example of what we do in terms of our algorithm. So comparing the brightness within the objects themselves. So this is part of the differential photometry technique that I mentioned earlier. When we do differential photometry, you're basically comparing your object, which is in this case quasar, with several other objects in the frame. And the reason you're doing that is primarily so that you can eliminate either atmospheric or potentially intergalactic phenomenon, which may cause variations in other stars. And some of them might be variable stars. So this is why you compare one object with several other objects in the image. Because you don't want, if you get a variable star, for example, it could skew your results. So you compare your quasar with most of the objects in there that you can see above a certain photon count. You will be comparing. Now, you generally want to keep them close enough in terms of brightness and close enough in terms of color content, frequency, basically, wavelength, if as possible. But in saying that, we would generally use pretty low cutoff frequency filters. So, but it is important nonetheless to keep an eye on that. And then we produce the light curves, which is the end result, which is what I'm going to talk about in a moment. So, as I say, and I appreciate I'm probably pushing time slightly, but so we develop software calibration techniques. So we go from I am going to read this out: image correction to source ID. We center it, we match it, and then we extract it. But one of the first part of that is actual calibration. So when it comes to calibration, on the right-hand side, a typical optical flat field. So this is a typical image that you would get from any optical train. So if you're using optics at all, this is something that you're going to be pretty familiar with, because this is what a flat field is going to look like. So this is the result of the likes of tiny dust rings and droplets and so on your actual optical train. So and what this does is it creates an unusual field whereby you get different responses on your imager to photons that are coming onto it. So you need to calibrate that out, and you need to calibrate that out regularly. Usually you'd actually probably have to do it on a nightly basis, ideally. Preferably done, there are two methods of doing it. You can do it either at dusk or dawn, or in our scenario, we can potentially do it on the inside of the dome, where we have a system whereby you point the telescope at it and you can do a flat field off that. But that's not necessarily for everyone. Normally it's at dusk or dawn, but as long as you have a consistent background light that you can see where the dust rings are, if you can take that kind of image, you can calibrate that out. But flat fielding is very important, because the response of each pixel to the photons that are arriving on it is very important to understand. So you always want to front load the calibration side of it. It's best to know in the first instance whether it's optimized or not. So that's why we do the flat fielding, and we obviously also do the bias correction, the zero bias correction, the dark field correction, dark pixel correction, and so on. So here's just a couple of images, and I've only a couple more slides. So here's our telescope at Blackrock Castle Observatory on the left-hand side. So this is a 0.4 meter. And here is where we kind of test. So we take our exons, and we actually have 6 exons in total at the moment. So we take our exons, and we plug them onto the back of this particular telescope. We test them. We test our software platform and we test our hardware. And then on the right-hand side, the 2.2 meter at Calar Alto, which is just outside Almeria in southern Spain, there's actually, you can see there's an Exxon on the back of it. We take our hardware and we take our software and we go to that particular location, and we will do some deep sky imaging, deep field imaging. So that's kind of what we do here. So source identification, we used the OTSU technique. Although we did actually modify it slightly. We modified the algorithm slightly in order to extract it. But you can see that basically we're using, again, using profile fitting to the two peaks in order to extract where exactly the inside and the outside is. So what does that all lead to? So I mentioned light curves. So this is a typical light curve using standard techniques. So you can pretty much see here, importantly, you'll notice that the error bars are, certainly towards the end are reasonably large. So they kind of would suggest that your certainty on what you're doing is not great. But they are empirical error bars, and that is important because empirical error bars would suggest that at least you're working off actual data as opposed to theoretical data. So this is the same plot. And now when we apply our technique, which is known as Lucky Phot, you can see a completely different graph. So we were able to, and this is an exoplanet, by the way. This is not a quasar. This is HD 18933. So we were able to extract the light curve. So the dip that you're seeing is effectively where the occultation is happening. So the planet is passing in front of the star itself. But you'll also notice that the error bars are significantly lower. So our certainty is better. The Lucky Phot system itself is based on the fact that we take snapshots which are the closest in accuracy, and we combine them. And by the closest in accuracy, I mean the closest in terms of atmospheric similarity. So we take atmospheric results. So the atmosphere is always variable. You always get adjustments and things going on. So we take the ones which are most similar in atmospheric accuracy, and we combine them to make a better picture. And that's what we see when we look at Lucky Phot. And it tends to lean towards basically taking out some of the noise and bringing in and maintaining some of the best signal that you have, and comparing that, which will give you ultimately the best light curve itself. So that's just one technique. We have many, but that's just one technique. So you can see here a typical system that we normally develop. So we put the likes of an Exxon or an SCMOS, which we've used a couple of times now at this point, an Andor SCMOS, and we put them. We use the capture, so we put them on the back end of a telescope. We record the information. We simplify in terms of we calibrate, we analyze, we review it, we analyze, we review it repeatedly. Ad infinitum, as I know you're all very familiar with. And once we're comfortable or happy with the results, we then kind of archive it. And we repeat that process again and again. So that's kind of what we do. Now, when it comes to, and Niall will go into this in a bit more detail, but when it comes to, well, how does this all play into masks? You'll see a couple of more images that are actually very similar between what we do and what mask exhalation and efficacy are actually like. So with that, I'm going to hand over to Dr. Niall Smith. So Niall, if you're okay to take over, I will hand over to yourself.
Yeah, thanks very much, Al. So thanks for giving us the background on some of the work that we have been doing over quite a number of years, and using low noise, high readout imagers, and this is where our collaboration really with Andor, for going on for many years, has been extremely productive. So it's great to be able to talk at this conference. As Al said, we have been looking at point source images for a long time now, and back roughly this time last year, of course, the first suggestions that this COVID-19 was going to become a problem was starting to become evident. And so within our institution, which at the time was CIT, we've since become Munster Technical University, but last year we were Cork Institute of Technology. We decided, and part of my remit as head of research was to try to understand how we might address issues associated with mitigating the effects of COVID-19. So we set up what we called a research solutions group. And the rationale was clear in the title. It was a group to look for solutions. How could we, as a public health response, use the combined efforts of the researchers in our institution and also researchers that we would collaborate with. So we know this is a global pandemic, so it needed a global response. So we set up internally in the first instance this research solutions group. It was multidisciplinary. We had astrophysicists, biologists, business people, engineers, photonics people, and a number of virologists as well. The ethos was simple. Let's brainstorm. So we started the meetings, and this is now going back, as I say, just over a year. It's important to remember that, because a lot has gone on in the last year, and we're probably taking things for granted now that we didn't take for granted last year. So ask you to sort of cast your mind back to how we were imagining things this time last year. So the ethos of this group was to brainstorm, to throw ideas out there in a multidisciplinary way. Nothing was off the table. There was no question or suggested solution which was in any way silly. And what we were looking for was to try to see is, when we threw these ideas around, did something fall out of the woodwork? The approaches that we were addressing had to be disruptive. So we realized that there would be a lot of sort of incremental improvements to addressing COVID-19. We were interested to see, was there something we could do that was disruptive? Many of you will be familiar at the moment, the kind of the idea of disruptive technology is sort of very de rigueur. So we were in this idea of, let's try to be a bit of a step change. And it had to be solutions driven. So as I say, incremental was not particularly of interest to us. So that was the basis on which we kind of started the discussion. And we knew that there was a funding stream becoming available, which was Science Foundation Ireland, their COVID-19 rapid response call. And of course, if you're a researcher, then having a funding stream is critically important, because we didn't want these conversations just to be conversations. Importantly, at the time, there was a lot of access in an open science sense to information. But also some of the things that information was addressing was something of a surprise. So if we look at this from March 2020, how to prevent the spread of COVID-19, we have 4 different elements to it: wash, cover, avoid, and clean. But actually, in Ireland, the emphasis was all about washing your hands, avoiding contact with your eyes and so forth, and making sure that you're disinfecting very, very regularly. But the comments and the discussion at this time around cover was really about covering your mouth and nose with your elbow. And it was, but we were looking at the literature, and we were looking at the literature as a multidisciplinary team, and really issues like singing, talking, ventilation really were not being discussed in any way by some of the in the public domain, but the literature was talking a lot about this. And so we were, as part of our brainstorming sessions, we were trying to figure out, okay, what are we missing here? Singing, talking, ventilation seems to be important, but government health advice doesn't appear to be in line what we perceive to be the up-to-date science advice, and actually advice that had been around for a long time. And some of you on the call may know more, because as Al said, myself and Al are not virologists, although we had virologists and have virologists on the team. But it was very clear by even as a physicist looking back, that there was a lot of information in the literature already about airborne transmission of disease. And there had been various different mitigating mechanisms used by countries, particularly in Asia, to address different outbreaks in the past. So we were kind of bemused and surprised as to why there wasn't more conversation around this. Then at the same time, we had a program by a very popular presenter, Pat Kenny. Some of you may know him, depending on where you hail from. And I happened to be listening to this in the car, and this is about sort of the random access to open access to information. And he was interviewing a gentleman whose name I don't remember, from the Czech Republic, who was talking about how they were making masks, and they were making them in homes and so on, because there wasn't enough PPE at the time. But they had this idea that, taken from previous experiences in other parts of the world, that masks would probably be a good thing to have. So this got us really interested about the idea, because there really wasn't much conversation in Ireland at the time, as I say, about masks. So this got us really interested, and we did a little bit more digging into the literature and asked essentially the question, well, what's all this fuss about masks? Is there anything in it? And is there anything in the idea that you could use commonly available materials as masks? Did it have to be PPE? So there was, in our interpretation, this sort of sense that if it isn't something that's at a very high level of efficacy, then it's probably potentially not that important, and we should really be more concerned about cleaning surfaces and not touching hands and eyes and so forth. But one of many diagrams that we trawled through as a team, and this was one that really stuck out with us, which is a model independent assessment of what happens if you have, in this instance, on the x-axis, the efficacy of a mask. Actually, that can be anything which minimizes transmission. In this case, we're talking about masks, but it can be anything which prevents the airborne transmission, or indeed, it doesn't even have to be airborne. Technically, it's just stopping a virus getting from A to B, where it can continue to replicate. So that's on the x-axis. On the y-axis is adherence. So it's the percentage of the population that are actually wearing. I'm just going to say masks from now on, even though, as I said, it's independent of whether it's a mask or not. It's the percentage of the population that are wearing masks, and the relationship between that and the efficacy of the mask. We've put in two red lines, a vertical and horizontal, where they overlap. The reproduction rate in the graph is 1. So you can probably see the blue area, just as it starts to get blue, that indicates the reproduction rate has been brought to 1. If you move up towards the top right of the graph, so you're moving towards efficacies of 100% and adherences of 100%, then of course, if nothing gets through a mask and everybody's wearing masks, if they're 100% effective and everybody's wearing them, of course, then there's no onward transmission. So this assumed that the starting reproductive rate was 2.4, but which was a reasonable estimate at the time of COVID-19 from the literature and from public health advice. So if 60% of the population wore masks that were 60% effective, then we would reduce the reproduction rate to 1. So while that doesn't stop reproduction, of course, but it does kill off the exponential increase in the transmission. So that looked really interesting to us. So we then were thinking, well, okay, if this is the case, can we look at readily available materials? Because it was clear that the medical grade PPE materials was in short supply and was needed by frontline workers. Can we somehow look and examine readily available materials to see how good they are? While we were doing that, we were invited to participate in the National Standards Authority development of a regulatory a regulation for the manufacture of masks, so SWIFT 19/2020, and this was done in March, April 2020, as you'll see on the slide. So very early on, we were already starting to talk with our National Regulatory Authority about the idea of helping them to develop standards for mask production. But Alan mentioned something about the going back now to what Alan was talking about, star fields. If we look here on the right, you have a typical star field. We'd all be familiar with this, and Alan has already showed this. And on the left, this is what a cough without a mask looks like. This was a little video that actually went viral at the time. It was published on April the 15th last year. And when we looked at it as part of our brainstorming group, we thought there's a clear overlap between these two, at least to first principles. They look very similar. So we thought, if we can measure the brightness of the dots in a star field, we can measure the brightness of the dots in a cough field. And then the question is, can we calibrate that brightness to tell us what are the sizes of the droplets that are causing those images, those bright spots in the cough images? So it's a very simple idea. We were thinking, as astrophysicists, as Al has indicated, we can measure brightnesses. We know we can do that. So we don't have to develop those algorithms. The question is, can we apply that to the coughing without a mask? So that's what got us interested, because we felt we didn't need to start from ground zero on the development of the photometry side of things. We just needed to determine, could we apply it in a new domain? While we were doing that thinking, we published a paper on the 15th of May, which I like the title of, always have, COVID-19 in the absence of vaccination, mask the nation. And it was based really on that simple previous graph that if you put a lot of masks in, even if they're not 100% efficacy, then you have a significant chance of reducing the reproduction rate. So it seemed like this was something that should be done. We were concerned that the emphasis was on washing and cleaning and so forth, and there wasn't enough emphasis on airborne transmission. So in terms then of dissemination and impact, just becoming for the next couple of minutes, of course, when you get funded, there's always this question, and I will come back to a little bit of the experimental setup in a second, but about what's the dissemination and what's its impact. Well, on a very local level, we generated, back in August 2020, we made a decision in our own institution that masks will be mandatory. In fact, we made this decision really in much earlier than that. We probably made that decision in June, but we told students and staff in August that it would be mandatory. Now, that wasn't the national public health advice at the time. That was advice that we determined based upon the research that we were doing, which was based upon what I've just described. So the application for funding to Science Foundation Ireland. So these are then some of the early images that we took when, so we did get funding, I should point out. And what we did was we took a medical dummy head, and we used a 10% sodium chloride in water solution, which we exhaled through the dummy head. In these images, you can see that on the left, the dummy head is not wearing any mask at all. You can see emission vertically and roughly horizontally. When you wear a mask under the nose, you can see emissions both vertically and horizontally. This was something that was a little bit of a surprise to us initially, but the mask actually acts as a reflector. And so under the nose appears to be almost as bad, if not worse, than no mask at all. You still get a forward movement of the sodium chloride. These images were taken with an Andor Soma 2K by 2K camera. And before showing the third one there, where you can see there is a mask, the blue light is a laser which is curved around the face of the mask. This is something which we hadn't seen before. And we also have a second laser line, a laser curtain, which is showing in red here. And that gives us the emissions perpendicular to the face. So up and down is a curved laser sheet, and perpendicular to the nose, mouth, direction is a flat laser sheet. So we were able to estimate where the leakage comes from. Now, we couldn't estimate, and we still can't, all the quantities associated with that. That turned out to be a more difficult problem. So exactly how much of it goes in the forward direction and how much of it goes in the up and down direction. Obviously, the third image there shows there's less of emission overall, and there's a relative quantification in the three images, but it's not an absolute quantification. We did a couple of publications around this. This was just a paper, a conference paper that we did around fabric or fit. And really what happened, and this is why this becomes important as we come towards the conclusion of the presentation in a few minutes, that we realized that fit really complicated the issue of fabric. So early on, we were really interested in what's the efficacy of a material. But the efficacy of the whole system is, of course, what you really need to determine. And the problem is that we were finding that the efficacy of some masks, because of fit, was the dominant problem or the dominant positive thing. Now, in PPE, there is a fit test as well. So if you do medical grade, if you have a fit test as well as a material test. But our original thought was, well, can we just test the material for widespread use? Remember, the rationale was there won't be enough PPE for everyone, and we're already starting to see people in various different places making their own masks, sometimes selling them, sometimes people just doing it in their homes. So we were kind of keen to know, well, how good does that, does cotton material work versus other things? But the problem was that as we went through the initial stages of analysis, we realized that question on its own is really not very meaningful, because you can have if you have a PPE, a perfectly a material that's 100% effective and it has holes in it around the sides, to take an extreme example, well then it's actually not 100% effective. So while I might be stating the obvious in one sense, it actually becomes very evident when you start to look at the images. Nevertheless, when we were talking about images, we did submit an image for the Science Foundation Ireland Research Image of the Year Award, and we were lucky enough to win that. We called it Talking Heads, for those of you who remember the group. Then you're of a certain vintage. And in it, the idea was that you don't have to explain it. There's a clear disparity between when you wear a mask and when you don't wear a mask, and this has been widely publicised, and we're very pleased about that. It's a side shoot of our original work. We didn't start out by thinking of having this particular type of approach. So in terms of the image, I just want to show you one image from our analysis. If you look at the bottom right, you'll see a kind of a circle, and inside that, I hope you can see there's a lot of dots. Those dots are actually polystyrene particles, which we have exhaled. They're not water-based now. They're polystyrene particles of known size that we have exhaled through a mask. We changed the mask material and so on. So we have started to estimate how many of these polystyrene particles get through the material. Now, this is an ongoing research, because, of course, water it doesn't behave the same as it penetrates material as a solid substance like polystyrene, even though polystyrene has a slight malleability about it. But we can measure very accurately the brightnesses of each of those dots that comes out, and I hope you can see them well enough to see that there are individual dots. But if you do look closely, you might see some of them are slightly elongated, and the issue here is around making sure that the droplet, I'm going to call it a droplet, even though technically it's a polystyrene in this image, that the droplet actually goes through your laser sheet, because you're relying on it going through a laser sheet and picking up the light that it reflects as it goes through the laser sheet. In the case of a droplet, there'll be some internal reflections as well, but you're relying on that to be a measure of the size of the droplet. And that works if the droplets go perpendicular to the sheet, but if they run up along the sheet due to thermals, even a little bit, then it complicates the analysis. So we're still trying to really get to grips with that, and on top of that you have some of the fit issues as well. So but just as a second last slide, we can now take the images from the previous slide, using, we've used both our own data, and I didn't say it in the previous slide, but I won't go back. We use some of the Andor IMRIS software extraction software as well, because that does certain things that our point source software extraction methods don't address. But when we run it through both the Andor software and our own, we get a consistency in the output. Unfortunately, we're missing a last slide, which would have shown the distribution of droplet sizes. And what we're seeing is something when we do this in relation to purely the polystyrene, what we see, and as I said, it should be on a slide, but unfortunately that slide isn't here. I can see it's not here. The brightness of those polystyrene, because they themselves have a very small range of sizes, we would expect that the brightness of those as they come through the material should have a very small range of brightnesses. At the moment, we're finding that the spread in brightnesses is larger than we would at first expect, and we know that's because we've got these movements in the thermals, so we know we've got a bit more work to do to remove those what look like streaks from the data set. But we can get consistency in the measurement of the photometry at least. And so what are the take homes? Well, one thing, high speed, low noise photometry is highly flexible. You can use it in astrophysics, you can use it in this instance in virology, and we're really interested now. We've got really interested in the whole area of airborne transmissible diseases and how we might detect those by measuring brightnesses. The brightnesses in the second bullet point here, we've mentioned we can detect 2 to 5 micron droplets. We know we can do that. We think we're pretty sure we can do smaller. We could certainly do smaller if we used a brighter laser, because you simply get more scatter from a brighter laser. But the great thing about being able to use either Exxon cameras or SCMOS type cameras that we have from Andor is that both have a noise threshold which is close to 0, so we're really just photon limited. So you can't really argue at that. I mean, your experiment then at least isn't being negatively affected by the performance of the camera. So high speed is important because in their photometry, if we want to remove atmospherics, if it's astronomy, and if it's in masks, then we need to be able to detect these droplets as they go through a laser sheet. They're only going to spend a few milliseconds going through that laser sheet, and so we want to try to capture them during that time period. We don't want to integrate beyond that. Finally, the last 3 things, multidisciplinary teams, really important. You're probably all involved in them, but it's just another example of how a random thought process back in March 2020 led to a whole new series of research for those of us who have an astrophysics background. We also then, the second last bullet point, fit and fabric are critical parameters, and that's complicated from our perspective. The measurements we had originally hoped to make, that makes it in one sense exciting for us, but it's also challenging because we now have to decouple the fit efficacy from the fabric efficacy, and then you can introduce a whole load of matrix into your matrix of possibilities, like as fabric becomes relaxed over time, or if people do a lot of talking, what does that do to the fit and so on. So this is something that really needs to be assessed in the longer term to really understand fit and fabric in readily available maybe not medically grade fit masks going forward. So we really need to understand what is the likely efficacy of the mask itself. Adherence is easier to measure. Going back to the graph I mentioned earlier, we can pretty much know if 50% of the population or 60% are wearing them. We can probably measure that more easily. But this fit and fabric is going to be tricky going forward. And finally, of course, wear a mask. That is something that we've all, I think, learned since March of last year. And as a final comment, I remember the first time I went to a shop wearing one, and it just felt so bizarre to be doing it. Now you go into a shop and you're not wearing one, and it feels, not only does it feel bizarre, it feels positively unhealthy. So how much we have changed in a year. So I'm going to leave it at that and hand it back to Alex, I think.
Hello, thank you both very much for your talk. We will now go ahead and take some time for questions. And it looks like we have have already had a number of questions come through during the presentation. And just a reminder, it's not too late to submit a question. You just type it into the question box in your control panel. So the first question we've had through is for Alan. Does high-speed photometry remove all of the issues caused by the atmosphere, or is there a limit?
It doesn't remove all of it, but it can certainly approach the limitations thereof. You will get absolute limitations when it comes to ground-based photometry and ground-based telescopes in comparison to space-based telescopes. But using the techniques that we're currently developing, you can actually approach the similar limitations that space-based telescopes. But ultimately, it's not going to be it's not going to actually hit that particular target. But you can get there. But importantly, the reason that we would choose to do this is it's a lot less expensive to develop a telescope and instrument system on the ground than it is to put it into space. When you have the James Webb Telescope, which is billions of dollars, and the Hubble Space Telescope, which is billions of dollars, and so on, there's a lot of money going into that kind of stuff. But that there are also plans for the likes of the European Southern Observatory, who are building telescopes, building a particular telescope, the ELT in Chile at the moment. These type of high-speed imagers on the back end of the ELT, for example, would give extremely good results. So if you couple that then with the software techniques that we're developing to reduce the impact of atmospheric turbulence on the images, would, in theory and hopefully in practice, because it hasn't been tested yet, obviously, would herald significant results.
That's great. Thank you very much. I have another question here for Niall. Face shields are not covered, yet they are commonly used in food preparation areas. Are they acting to simply redirect the aerosols?
Yes. So face shields really are they give this sense of protection, but the questioner is exactly right. All they do is they just reflect it down. We just don't use them. Yeah, they really perform no useful function other than the face-to-face. You'll see them obviously sometimes used in association with masks, but in food preparation, the concern one would be is that it actually brings it down onto the food itself, and they are quite effective at that reflection as well. There have been some studies about whether or not your average aerosol moves downwards or sort of sticks to the fascia. It doesn't. It moves downwards because it's carried in the airflow. So before it even gets there, there's a kind of a pressure wave built up between your exhalation and the front of the face mask, and that redirects most of it down. Larger spittle might end up on your face mask, but that is something that's not what we're mostly concerned about.
And we have another similar question here. Did your team consider the interaction between mask material and with virus and associated materials in nasal drop in the context of physics?
Can you ask the question again? So just so I understand it, because I want to try to give obviously an answer that makes sense to the question.
Of course, yeah. Did your team consider the interaction between the mask material with the virus and associated materials in nasal drop? In the context of physics?
No, we didn't. Although we have actually talked to some other groups who are looking at aerosol physicists, for example, and how. So if I understand the question correctly, that's why I was asking again, because I wanted to try to answer that. Nasal drops have a different viscosity, for example. So once you start to introduce, like, what comes out our mouth is actually quite complicated, or our nose, and it's different. So we haven't looked at that yet. There has been some conversation we've had with another group. It's one of that part of that matrix of things that needs to be considered going forward. But unfortunately, no, I can't be helpful there. We haven't so far.
I have a similar question along the same lines. There are a few questions discussing, do you have any plans to use an alternative solution to either the sodium chloride solution that you discussed, for example, a solution that is representative of saliva, and also another question on, are you planning to use bacteriophages to test the masks as well? So along the similar lines as the previous question.
Yeah, so on the bacteriophages, it's probably more for the biologists in our multidisciplinary team who aren't present here at the minute. So we have actually done some analysis of the growth of bacterial deposits on the mask material itself, as distinct from ones that are transmitted through it at the moment. So again, if I understood it correctly, and the first question was yes, we actually we plan, but we haven't done. It's actually in our proposal to use real people, for want of a way of putting it, rather than just dummy heads, in order to try to see what the efficacy is. To do that, we believe we need a large number, a large sample on which to get sort of an assessment. And at the moment, we simply can't do that with the way that access is restricted to labs, plus all the other different public health issues. We don't have the clearance. We're not allowed to do that. But it is something that we would plan to do. Our original plan was to use healthy individuals to talk through the materials, but we moved towards dummy head because of restrictions. And I know some facilities have more ability to do that than us, but we don't. But we're not allowed to do that yet.
Of course, yeah. And I have another question here on, would the close-fitting fabric work more effectively as droplet size is larger at the source?
The close-fitting fabric will always work more effectively with up to a point, depending on the permeability of the fabric. Obviously, you have to breathe, and so you have this kind of optimization curve where if you make the fabric too effective, then people breathe heavily, and then they actually overcome the issue. And what we have noted, and we haven't measured this directly, we noted the velocities, but we haven't used, and we noticed them in the literature. So we can measure velocities coming out, and what we've noticed is sometimes the velocities are higher. So you have a smaller number but higher velocity. So in principle, the danger that by going to masks which actually are in principle very good, you end up with a higher velocity, although lower volume output, which in principle can spread the virus in the first instance farther, or the droplets, I should say, farther in the first instance. So we're trying to understand as well where the sweet spot is between breathability, and emission of the droplets. Apart from the fact that if you make masks uncomfortable, they just won't get worn. And adherence is such an important part of this that we have to make sure that people will wear them.
Of course. Well, thank you very much. I think that's all we have time for today. Thanks to the audience for all of your questions, and we will get back to any unanswered questions individually. We really appreciate you being here and attending our virtual event. A recording of this webinar will be available in our Learning Centre on andor.oxdents.com from next week. Please be sure to check out our website and get in touch if you have any further questions. Thanks again for joining us today, and please enjoy the other presentations on offer.